Alright everyone, good morning. We're going to be doing lesson 114, which is going to be 3x3 systems of equations. To solve a system of equations in 3 variables known as 3x3 systems, the primary goal is to eliminate one variable at a time to achieve back substitution. 3 possible solution scenarios for a 3x3 system exist. One solution, no solution, or infinitely many. So it's just like the 2x2s in that aspect, okay? So there are these steps that you can follow to kind of talk through like what to do if you're stuck. But I would like you to try to be intuitive about it, because that's the way that you're going to remember how to do it. So I try to always teach you to be intuitive, because if you try to memorize steps, that just makes it hard for you to know how to do it when you don't have all the stuff in front of you, okay? So let's look at a problem and I'll talk a little bit about that. So the first scenario that happens is you have a system with one solution. Now when you have one solution with a 3x3 system, this ordered pair is going to be like x, y, y, z, okay? Because if I'm adding a third variable in, I'm no longer in the 2 dimensions. I'm now in the 3rd dimension. So all of these problems deal with 3-dimensional objects, okay, or shapes or lines or planes. So usually you're dealing with x and y, which are the vertical and horizontal axis. Now we've put in depth, okay, the depth, which is the z. So all of these equations, each one represents a plane. And planes are 3D objects. So you can think about a plane as like a piece of paper in space that's infinite, okay? It has depth, it has length, and width, okay? So that's what each of these equations represent. So if you think of the one in the yellow as the first equation, the one in the green as the second equation, and the one in the blue as the third, what that means is they can intersect at a single point, and they will only ever intersect all 3 at a single point at one time, and that's when they have one solution. So does everyone see that there? So we're going to learn how we find those solutions. So if I zoom into this problem right here, first thing I always want to check is see if there's any of these 2 equations I can add together that will cancel out one of the variables. And in this case, I can't see one. So if I add these 2 together, these x's don't cancel, these don't cancel, and so on. So that doesn't seem like that's going to get me anywhere. So when that's the case, I'm going to go for another procedure, another method, okay? So the other method I can use is substitution. So to do substitution, I look for a variable in one of the equations that has a coefficient of 1 or -1. Does everyone see that right here? Good. So whenever you find that equation, whether it be the first, second, or third, your goal is going to be to isolate that variable, okay? So to isolate the x or the z, I'm going to add the z to both sides. That's going to give me -5x plus 3y equals z, I'm lagging a little, sorry, z minus 17. And our goal was to isolate the z. So what would I do with the 17? Good. Add it to both sides. That's going to leave me with -5x plus 3y plus 17 is equal to z. And I always put a line through my z because they can look really similar to 2's. So I just want to make sure they're differentiated, okay? So what I have now is a tool that's going to help us through the other 2 equations. I now know what z is equal to in terms of the other 2 variables. So what I can do is, in those other 2 equations, I can plug that expression in for z in the other 2 equations, okay? So that's exactly what I'm going to do. And when I do that, I now will only have 2 equations in my system instead of 3. I'm sorry, 2 variables in my system instead of 3. So I'm going to take z and replace it with this right here. So I'm going to rewrite this first equation, but I'm going to be replacing z with this. So that's going to give me 2x plus 4y minus 5 times what z is equal to. And I'm writing small because it gets pretty big here. You'll see. Is equal to 18. So does everybody see what I did there for the first equation? I replaced the z with what z is equal to.
Can you give me 1 second?
Yeah, you're good. I'm going to keep going, but it's going to be on the board. So the next step, once I plug that in, is I'm now going to simplify this as we usually do with math. So I'm going to use the distributive property here, okay? Now, my suggestion is, like I said, these are really prone to error. There's a lot of moving parts. Use a calculator, okay? There's no shame in using the calculator to do these operations. Don't try to do anything complicated in your head. That's where you can make a mistake. So, I'm going to distribute. I'm just going to bring down the beginning here because nothing happens to it. Negative 5 times negative 5x is positive 25x. Negative 5 times 3y is negative 15y. And negative 5 times 17 is negative 85. And that's all equal to 18. So is everyone with me on how I got from that step to the next? I just distributed. Now from here, I want you to combine like terms. So I have like terms here, here, and here and here. So that's going to give me 27x minus 11y is equal to. Now I'm actually going to add the 85 to the other side. And there's a reason I'm going to do that. Because now we basically have an equation of two variables. And it looks really, really similar to the equations we were working with in the 2x2, right? So that's going to come in handy later. We're going to come back to it. It's going to be useful. However, we are also going to need to deal with this equation right here, and we're going to have to plug in for z, right? So we're going to do the exact same thing we just did for the first equation to the second with the information that we have for z. So I'm going to rewrite my second equation. But instead of z, I am going to write what z is equal to, which is this expression right here. So I rewrote it, but I plugged in for z. Now I'm going to use the distributive property here. That's going to give me negative 3x plus 5y minus 10x plus 6y plus 34 is equal to negative 27. I'm going to combine the like terms as I find them. Bless you. That's going to give me negative 13x plus 11y is equal to, and once again I'm going to subtract my number over so that I have standard form. And that's negative 61. So now I have another 2x2 equation. So does everybody see what I highlighted in the yellow and the green? You see now we basically have a system of two equations like we did with the earlier 2x2s. Now from here I want you to just take a second and think of how we solve 2x2s. We use substitution and elimination. So I want you to look at these two equations right here. Which one do you think would be better here? If I canceled out the
y
by doing what operation? Elimination. So what I'm going to do is I'm going to take this one right here and I'm going to write it underneath this one. And this one might be a direct elimination where I don't have to multiply by anything. Does everyone see that? Because what's going to happen when I add these two equations together? The y's are going to cancel out. And that will leave me with 14x is equal to
42.
Good, 42. I just combined these. And then I now have information sufficient to solve for x. And x is what? 3. So that's going to come in handy in a second, the x. So is everyone able to understand what we just did? And I will go through the procedure again at the very end. So now that we have x, remember our goal is to solve for x, y, and z. So if I take one of these equations, the one either highlighted in the yellow or the green, I can plug in for x and then solve for what? Y. Good. So I'm going to take the one highlighted in green, and I'm just going to replace the x with 3 to get the value for y. And I'm going to do that over here because it's hard to find room on here to do stuff, so to try to show you everything. That's going to give me negative 39 plus 11y is equal to negative 61. I add 39 to both sides. That gives me 11y is equal to negative 22. Divide by 11. Y is equal to negative 2. So now I have x, I have y, so what's the only thing left to solve for? Z. So the easiest way to solve for z is to use the equation isolated for z. And in this equation, I'm going to plug in for what two variables? X and y, which will then give me z, right? So I'm going to take the one in the blue right here, and I'm going to plug in for x and y. So we have y here, and I have x here. And now I just simplify. Negative 15 minus 6 plus 17 is equal to z. And that gives me z is equal to negative 4. So now I solve for all of my variables. Okay? So I'm going to zoom out. You can still see it, but it's going to be smaller, okay? So when you have a solution with one system, you need to write your answer like this. X, which is positive 3, y, which is negative 2, and z, which is negative 4. So it's always alphabetical order, but you have to put it in that order as an ordered pair. So it's a lot of steps, but they're not difficult steps. It's just tedious, okay? So was everybody able to at least follow what I was doing? Alright, so in case you were a little confused, I'm just going to quickly restate everything that happened. First thing I was looking for in the system of 3 equations to see maybe if I added any sets of equations together, if anything would cancel out. You can use regular elimination by multiplying by values, but I saw that I had a z that had a coefficient of 1 or negative 1, and I saw the opportunity to isolate it. Once I isolated that variable, I now had an expression that was equal to z that I could replace z with in the other 2 equations. Once I plugged that in and simplified, I had basically an equation with 2 variables and another equation with 2 variables, which was basically like solving a 2x2 system at that point. I solved that 2x2 system, in this case using elimination, and I got the value for x. Once I had the value for x, I plugged back into one of the 2x2s to get the value for y, and then I plugged x and y into the equation that equaled z to get z. Okay? So, luckily for you, this is the hardest one we're going to do on the notes. So the next one we're going to talk about is systems with no solution. So a system with no solution is basically where you have 3 planes that these 3 things can happen with. So each one of these equations represents one of the planes. It doesn't matter which color is which, okay? It's just a diagram. The first situation that can happen is 2 of the planes intersect, and then they intersect with one of the others and one of the others. So all 3 of them intersect with each other, but they never all 3 intersect at the same time. Does everybody see that? That's one situation with no solution. The other situation is one of the planes intersects the other 2 planes, but those other 2 planes never intersect each other. And the last situation is where all 3 planes never actually intersect at all. Now, yes, there is a way to actually differentiate these scenarios, but that's kind of for another course. If you're doing engineering or math in college, you will go more into this. But today we're going to talk about what no solution looks like in a system, and that occurs when you get a statement at the end that has no variables left that is false. And whenever that occurs in any process of your problem, you automatically know you have no solution. Kind of just like the 2x2s. So like I said, there's various ways to go about the problem. But the first thing I'm looking at is I want to see if there's anything that will eliminate right off the bat. And I'm not seeing that. So typically the next thing I will look for is a variable that has a coefficient of 1 or -1. And that's going to be the one I try to isolate. So because I have a z that has a coefficient of -1, I'm then going to isolate that z. So I'm going to rewrite this first equation. And my goal is going to be to isolate the z, however you want to do that. So to do that, I'm going to add z to both sides. That's going to give me -4x minus 2y is equal to z plus 15. And then of course I want to isolate z, aka get it by itself. So what would be my next step?
Subtract the 15.
Good, I want to subtract that 15 over, because when I do that, it's going to get the z by itself. So is everyone with me on how I isolated the z there? Now, once I isolate the z, I now have an expression that z is equal to that I can plug into both of the other two equations. Remember, I worked with this one. Now I'm going to plug that z into the first and second, or the third and the second other two equations. So I'm going to take this one right here, and I'm going to replace the z with what I now know z is equal to. Bless you. So I took that equation and I plugged in the value for z. I just double check my work. I make sure I didn't miswrite anything or anything like that, change any signs. And now, once I do that, I can now distribute here or simplify. Simplify the next step. That's going to leave me with -12x minus 6y minus 45 is equal to 45. Now at this step, you're going to combine like terms, of course. Everybody with me on this step here, where I am? Okay. So I have a few sets of like terms here. What happens when I start combining these like terms?
They cancel it out.
They cancel each other out. Does everybody see that? So isn't it true that 12x minus 12x is 0? And 6y minus 6y is 0? And that leaves me in the end with -45 is equal to 45. Is that true or false?
False.
Which means I have
No solution.
no solution. So what we know right away is one of these three situations is happening here. We don't know which one. You'd have to kind of further investigate. But one of those three situations is happening here, which means we automatically know we have no solution. Okay?
You don't need to find out which one of those three solutions.
Not in this course.
Alright. That's what it's wants to just find it.
Correct. Yep. You're going to like when these come up because they're less work. But be aware, if you had approached this problem a little differently, it might be true that you don't get to this until the second or third step. Because it might be true that you might have gotten one step to work and then the next might not. So it just really depends on how you approach it when this comes up. Because it could be true that you worked with the first two and they intersected, and then the next one didn't, right? Okay. So now we're going to talk about a system with infinite solutions. This means that the number of solutions that these two have never ends. Okay, there's infinitely many of them. And this can happen in two ways, okay? The first way that I'll talk about is the more simple one. This is figure 2. This basically means that these three equations represent the same exact plane. So it's basically like me having three pieces of paper on top of each other. They're basically the exact same plane with the exact same points. They contain all these same points. The other way this can happen is that you have the three planes intersect, and these planes have infinite depth and width and everything, so they're going on forever. Think of it as going on forever this way, okay? That means that the line that goes through it is infinite, and it touches infinite points. So you know the expression where they talk about how some infinities are larger than other infinities? This is one of those scenarios. So the plane basically has more points in common than the line, but they still have infinitely many options, okay? And all you need to know is when it's infinite, you will get a true statement with no variables left, such as 0 equals 0. So let's go ahead and look at these systems and see what happens. So when I look at these three systems, I see automatically I don't have any coefficients of 1 or -1. So this may require me instead to use elimination for all the steps. Now I want you to take a careful look at equation 1 and equation 3. What do you notice about these two?
You got a variable that can cancel out.
I have a variable automatically that will cancel out, right? Which variable? Z. So what I'm going to write, and this is kind of helpful sometimes to keep organized, this is what you do in linear algebra. I'm going to say I'm going to take equation 1 and I'm going to add it to equation 3. And the reason we say that is just helps us keep track of all that math that we're doing. And then I'm going to line them up and add them. So it's really common to number them. So I rewrite equation 1, I rewrite equation 3, and then my goal is going to be to add them together. Well, that's going to give me -11x minus 12y equals -6, because these go away. So now I have a 2 by 2 equation, and you're going to kind of come back to it later once we can work with it. All right? So is everyone good with how I added these together and what the purpose of it was and where it got us? Okay. Now in order to get information about x and y, we will have to get another equation that has just x and y. So what I want you to do is to look at equation 2 and equation 3. What could I multiply equation 3 by to get it to cancel the z in equation 2? 2. So what I'm going to write is I'm going to take equation 3 and multiply it by 2 and add it to equation 2. So I'm going to take equation 3 and multiply it by 2. And once you get really good and comfortable with this process, you don't have to write the distributed property out every time. You can just go ahead and multiply. It's up to you. It just makes sure you, whatever works at your comfort level with this. So I'm going to take my third equation, multiply it by 2. Make sure you multiply every single term. And once I do that, I'm going to then rewrite my second equation underneath it, because remember, our goal is going to be to cancel these out. Now once I have that written out, I'm going to add these together. That gives me -33x minus 36y is equal to -18. So now I basically have two 2 by 2 systems, right? So we have many options on how we choose to solve this. So before we go ahead and solve the 2 by 2, does anyone have any questions about either of these two steps? Okay. So now I want you to think, what can you multiply this equation by that will allow you to cancel out the x and the one shaded in pink? 3 is close, but we want the signs to be opposite, so I'd have to multiply it by -3. So what I'm going to do is I'm going to take this equation in the blue. It's my screen gets cut off. I did write the negative sign there, but it's getting cut off. Hang on. Let me write it further over. There it is. -3. And I'm going to multiply it by this equation right here. That gives me 33x plus 36y is equal to 18. And now I'm going to rewrite the pink equation underneath, and you're going to see why. What's 33 minus 33? This one becomes?
0.
And this one becomes?
0.
So I have 0 equals 0, which is a true statement, which means that there are what to the solution?
Infinite solutions.
Good. So the system has infinite solutions. Alright, how did everyone feel about that?
Takes a while.